Yeah, good afternoon, Virendra. Good afternoon. Am I visible and audible? Just let me know in the chat box if I'm visible and audible. Can you able to see my screen? Hello, are you there? Hello, am I audible? Hello, Virendra, are you there? Hello. Yeah, good afternoon. Am I visible and audible to Anjana Sri? Anjana Sri, can you hear me? Hello. Yes, yes. Okay. Thank you. Thank you so much. So let's start with the class. So I think in the last class, when I was teaching, I have took ionization enthalpy, right? So the physical properties of the thing we have seen, and the trends also we have seen, and atomic radius and ionization energy I have completed for you. And I think in the last class, you have completed the electron gain enthalpy and electronegativity part from the other sir, right? Am I right? Electron gain enthalpy and electronegativity was done in the last class. I think so. Am I right? If I'm right, just let me know in the chat box. Yes. So let me just quickly recap that electron gain enthalpy and electronegativity, and then I will move on to the next topic. So this is electron gain enthalpy. It is basically an atom will gain one electron, and while gaining this electron, the particular atom will lose its energy. Okay, so when this atom gain an isolated gaseous atom gains one electron, it will become fluorine will become F minus, and here if you see, the energy will be released. Okay, the energy exchanged when an electron is added to isolated gaseous atom in its ground state is called as electron gain enthalpy. So here the first electron is gained by this fluorine atom, so it is called as first electron gain enthalpy. An atom, a neutral atom, is getting converted into a gaseous anion. Okay, this is the thing. And since the energy is getting absorbed by the system, since the energy is released from the atom, it is called as exothermic process. It is an exothermic process, and the delta H value, if you see, it will be mostly negative. Since it is an exothermic process, it is highly negative, and you have to keep in mind that only the first electron gain enthalpy will be negative. The second and third electron gain enthalpy, they will be positive only. Okay. Now let me quickly recap the trend of this electron gain enthalpy across the, this is not across the period, it is actually for the group wise. Okay, it is the trend for group on moving down the group. There is a mistake, sorry for that. So the electron gain enthalpy trend on moving down the group is, you can see that for across the period also you can find, but group wise also it is given. And here you see, on moving down the group or across the period, first if I want to talk about the last element, the last group, the 17th group elements are having the more negative electron gain enthalpy value. When you go from here, when you go from this lithium to oxygen and to fluorine, fluorine is having the more negative value of this electron gain enthalpy. Okay, so on going from left to right, the effective nuclear charge increases. So that's why the delta H value is also more negative. Okay, the negative sign denotes the process is exothermic. Okay, you should not take it in the way you have seen in the max. Okay, don't take it in that way. That negative sign denotes that the process is exothermic. Since the heat is released from the process, it is exothermic in nature, and that's why we are putting that negative sign. Otherwise, you have to see only the number only. Okay, the number is very high for fluorine, right? So when you go from left to right, like ionization energy, electron gain enthalpy also increases across the period. Got it? Now on moving down the group, if you see, on moving down the group, we know that the atomic radius increases. And atomic radius and electron gain enthalpy, they are inversely proportional. If one increase, the other one will decrease. So electron gain enthalpy decreases on moving down the group. Okay, again and again I'm telling you, don't look into this sign. Okay, don't see the negative sign, just only see the values. The values are getting decreased. Got it? But there is an exception which you can find between this oxygen, sulfur, and fluorine and chlorine. Just look into it. I'll explain you that as an anomaly. Anomaly means some unique behavior. Okay, so there is some different behavior for group 16 and group 15. That is for oxygen, sulfur, and fluorine and chlorine. When you move from oxygen and sulfur, actually the value should decrease. Actually, the value should decrease. But between oxygen and sulfur, we can see the increase in the value. Okay, so oxygen is having the more negative, sulfur is having the more negative value, and oxygen is having the less negative value. And when you come to the 17th group, chlorine is having the more negative value compared to fluorine. So why? Why it is like that? Why the value is getting increased? Why the number is getting increased? It is because of its size. Okay, it is because of the size factor of oxygen and sulfur. So this is the, so this is the size of oxygen and sulfur and fluorine and chlorine. So we know that oxygen is very small in size compared to sulfur. Okay, so size of the fluorine and the size of the oxygen is very, very small. So when these two atoms gain an electron from outside, okay, so when I'm adding an electron from outside, when I add an electron from outside to oxygen and fluorine, that is electron gain enthalpy, right? So when I'm adding that electron repulsion would be there. Okay, already some electrons are present inside this oxygen and fluorine. So when I add one more electron, that electron and this electron, they will come closer to each other and they will start repelling each other. Okay, so the size of fluorine or oxygen is so small that electron clouded fluorine and oxygen cause repulsion with incoming electron. Okay, because of this repulsion, the addition of electron to oxygen and fluorine is becoming very difficult compared to the addition of electron to sulfur and chlorine. Okay, so if the value is more negative, it denotes that we can easily add an electron. We can easily add an electron to sulfur and chlorine, but we are not able to add an electron so easily to oxygen and fluorine. So that's why the process become very difficult and the value is very, very less. Got it? Is that okay? Anjanashree? And the other one? Okay, fine. Yeah. So which one will go for one question? Which of the following will have the most negative electron gain enthalpy and which is the least negative among phosphorus, sulfur, chlorine and fluorine? So let us solve this. We know that across the period, electron gain enthalpy becomes more negative. So if we want to see accordingly, fluorine belongs to the second period element and chlorine is below that and sulfur is before chlorine and phosphorus is before sulfur. Okay. Now, across the period, electron gain enthalpy becomes more negative, and on moving down the group, it becomes less negative. Okay, so chlorine will have the highest value. The exception with I have already told you. So this is the order. So this is the order. So hence, more negative electron gain enthalpy value is for chlorine, and the least negative is for phosphorus. Okay. So this is about the electron gain enthalpy. And next we will move on to electronegativity. So what is electronegativity? The tendency or the ability of an atom to attract the shared pair of electron towards itself is called as electronegativity. Okay. So there are two atoms, atom A and B, but atom B has a strong tendency to pull its shared pair of electrons towards itself. Okay. So now you see here, green atom is having the weak pull, and violet atom is, purple atom is having the strong pull. So atom B is having the ability to pull the shared pair of electrons in a covalent bond towards itself. So atom B is called as the more electronegative atom. Okay, so there are some scales, some numerical scales of electronegativity of elements from which we can get the electronegativity value for all the elements in the periodic table. So among those few numerical scales, we have two scales. One is Mulliken-Jaffe scale, and from this we can find out the electronegativity value, which is denoted by the letter psi using this formula. Sum of the ionization energy and electron gain enthalpy by 2 will give you the electronegativity value of from this Mulliken-Jaffe scale. And one more scale is there, which is called as Pauling scale. And we are using this scale only. Okay, you can find the electronegativity values in the periodic table chart, and there will be one value denoted under each element, and those values are in accordance with Pauling scale. Okay, so now from Pauling scale, electronegativity of each element, the values of each element is calculated using this formula from which we can get this. Okay, and now let us see the trend of electronegativity across the period. Across the period, you see here the value increases. So across the period, the value increases, effective nuclear charge increases, and electronegativity also increases. And the fluorine is the first most electronegative element in the periodic table. Okay, first most electronegative element with the electronegativity value 4 is fluorine. Okay, you should not forget that. Second most electronegative element is oxygen with the value 3.5. And third most is nitrogen and chlorine. Got it? Fluorine, oxygen, nitrogen and chlorine. So this is the trend across the period. Now the trend on moving down the group. The trend on moving down the group, if you see, size of the atom increases and effective nuclear charge decreases. So electronegativity also decreases. So across the period it increases, and on moving down the group it decreases. That's all. Okay. So this is a trend of electronegativity. And coming to the metallic and non-metallic properties, mostly non-metals, they always have the tendency to gain the electron. Okay. So non-metals in the sense, all the fluorine, chlorine, oxygen, they are the non-metals, right? So they have the highest tendency to gain the electron. So non-metallic nature is directly proportional to electronegativity. The one which is more electronegative in nature is more non-metallic in nature. Okay. And generally, if you see metals, what they do, metals always try to lose its electron. So metallic properties are inversely proportional to electronegativity. Okay. When the metallic property is very high, electronegativity is very less. Suppose if I want to take an example, I can take sodium. Sodium is present at the first group, right? Which is the very left corner of the periodic table, which is the electropositive element actually. Okay. So since it is highly electropositive in nature, it is very least electronegative, but it is more metallic. So that's why they are inversely proportional. Got it? So these two relations you keep in mind. And let us solve one question based on this. So 5 elements, silicon, beryllium, magnesium, sodium, phosphorus are given to you. You have to arrange these 5 elements in the increasing order of their metallic character. So how to arrange? Anjalashri, can you try for it? How can you try for it? So metallic character increases on moving down the group, and decreases across the period. This is the trend. So let me write the elements. Silicon belongs to third period, and magnesium also belongs to third period. It will be here, and beryllium is just above this magnesium, and sodium is before magnesium, and phosphorus is next to silicon. Now can you give me the order? On moving down the group, metallic character increases. Across the period, metallic character decreases. So who is having the highest metallic nature? Sodium is more metallic compared to magnesium, silicon and phosphorus, right? Moving down the group, it increases. So magnesium would be having the highest metallic nature. So obviously, first comes sodium, then magnesium, then beryllium, then silicon and phosphorus. Okay. So this is the correct order of the metallic nature, increasing order of the metallic character. Now let me quickly summarize atomic radius, ionization enthalpy, electron gain enthalpy. So atomic size, ionization energy, electron affinity or electron gain enthalpy, and electronegativity. So across the period and on moving down the group. Okay. So the atomic size across the period, atomic size decreases. And on moving down the group, it increases. The remaining three are just the opposite of atomic size. If the atomic size decreases across the period, all the other three, they will increase. And it increases on moving down the group, so other three will decrease. So this is the general trend for all the four physical properties. Got it? Now we will move on to the chemical properties and its trends. So till this you have completed yesterday. Now this is the new topic for today. So trends in chemical properties of the elements. So under this chemical property, we are going to discuss about the periodicity of oxidation state and chemical reactivity and some anomalous, that is unique behavior of the second period elements. Okay, from lithium to neon, those are second period elements, right? We will see the anomalous property of those elements, and then we can complete this lesson by today. So coming to the first topic, that is periodicity of oxidation state. So here I am going to start with the word valency. So what is meant by valency? It is the number of electrons in the outermost orbital. What is valency? Number of electrons in the outermost orbital is called as valency. Now if I want to take group 1, 2 and from group 13 till 18, the number of valence electrons of group 1 is 1. And it increases from 1 to 8. Okay. Suppose if I want to take an example for group 1, I can take lithium. Okay, lithium. And here beryllium. Group 13 is boron, carbon, nitrogen, oxygen, fluorine and neon. And for all these elements, if you see, the number of valence electrons will start from 1 till 8. Okay, neon has 8 valence electron, lithium will have 1 valence electron, and accordingly each element has valence electrons. And coming to the valency, so you see here, for 4 and less than 4, actually it is not 5, it is actually 4. Okay. For carbon, total number of valence electron is also 4 and valency is also 4. 4 and less than 4 valence electron containing species are having the same number of valence electron and valency. But when the number of valence electron is more than 4, then the valency and valence electron, it is somewhat differing, right? For nitrogen, you see number of valence electron is 5, but the valency is 3 for nitrogen. When you go for phosphorus, valency can be called 5 also. So it changes. And for oxygen, it is 2 or 6, and for fluorine, it is 1 or 7. For neon, it is 0 or 8, we can say. Okay. Now coming to the next word, that is oxidation state. Oxidation state of an element in a compound is the charge acquired by its atom after electronegative consideration from other atoms. So to understand this, we can take an example. I have taken OF2 as an example for you. Now here if you see two atoms are there. One is fluorine and the other one is oxygen. Now who is more electronegative? Fluorine is more electronegative compared to oxygen. So fluorine has the highest tendency to pull the shared pair of electrons towards itself. So fluorine, what it will do with respect to each bond, fluorine will gain one electron with respect to this left bond you see. So there are two electrons here in this bond. Fluorine is gaining that electron, oxygen is losing that electron. So -1 +1. And with respect to the right side bond, fluorine is gaining one electron and oxygen is losing one electron. So totally one oxygen is carrying how many charge? +2, right? So oxidation state of oxygen is +2 and the oxidation state of one fluorine is -1. Okay, the charge acquired by one oxygen is +2 and for one fluorine is -1, which is nothing but the oxidation number of that element in the given compound. Okay, so it is a charge acquired by its atom after electronegative consideration from the other atom. Got it? Now some more thing let us discuss. Carbon dioxide. So this is carbon dioxide. Now here also we have two different types of atom. One is oxygen and the other one is carbon. Who is more electronegative? Oxygen or carbon? Which is more electronegative in nature? Obviously oxygen, right? So oxygen, what it will do? It is having two bonds. So it will gain 2 electrons from carbon and takes -2 charge, and carbon will lose 2 electrons and it is gaining +2 charge. In the same way, with respect to the second right side bond also, oxygen will gain, carbon will lose. So each carbon, for that one carbon we have how many charge? 4+ charge, right? And for each oxygen we have 2-. So the oxidation state of oxygen is -2 and the oxidation state of carbon is +4. Okay, and oxygen shows two oxidation state in different compounds. That is two oxidation state in the sense two different oxidation state. Okay, generally oxygen shows -2 oxidation state only, but in few compounds it shows two different oxidation state. One among it is OF2. OF2 just now we have discussed, right? So in OF2, oxygen had +2 oxidation state. Now in this carbon dioxide, if you see, oxygen is carrying -2 oxidation state. So when this oxygen will show +2 and when it will show -2, it is depend on the atom to which it is bonded. Okay, so the more electronegative element will show the negative oxidation state. Here in case of carbon dioxide, you see, here oxygen is more electronegative than carbon. This is the electronegativity order, right? So here oxygen is more electronegative, so that's why it is having the minus value for its oxidation number. And when it is bonded with the fluorine, in fluorine if you see, when you compare fluorine and oxygen, fluorine is more electronegative. So in that case, oxygen is electropositive, or we can say less electronegative. In that case, oxygen will have positive oxidation state. Okay. So this is the order which we have to follow. Got it? Is it clear, Virendra? Any doubt from the periodicity of oxidation state that we have discussed now? No doubt? Okay. So the next topic is the periodicity of oxidation state. In that, we are going to see one tabular column. Okay, this is the sum of the hydrides of first group, second group, and from group 13 till 17. And this is the sum of the oxides of these group elements. Okay, so it is given in your book also. If you see, many elements, they show variable oxidation state. Okay, many elements also exhibit variable oxidation state, especially transition elements. Transition means all the D block and the F block elements. Actinoids comes under F block. So these D block and F block, they show different oxidation state. Okay, whereas these elements, group 1, group 2, group 13 till 17, they are exhibiting only one oxidation state. Suppose if I want to talk about this group 1, lithium is having +1 and hydrogen is having -1. Sodium is +1, hydrogen -1. Potassium +1, hydrogen -1. So in all the compounds of group 1, the group 1 elements are carrying only one oxidation state, that is +1. Okay. When you come to this 16th group, here for each hydrogen +1, so it is having 2 hydrogen, so +2, 1 for 1 hydrogen, -2. Here also -2 for 1 sulfur. Here also -2 for 1 selenium, -2 for 1 tellurium. So all the group 16 elements are carrying -2 charge. Only one number is given. But when you talk about transition element, that is D block and F block, they will have multiple oxidation state for single element. So that is their unique behavior that we will discuss in class 12. Okay, in class 12 next year you will study. Now I'll go with one question. So using the periodic table, predict the formula of the compound which might be formed by the silicon and bromine atom. How to find out the formula of the compound from silicon and bromine? So to predict the formula from the given element, you have to look for the valency. Okay. Now the first element is silicon. Silicon belongs to group 14. And the valency of group 14 is 4. Valency of group 14 is 4. And the valency of bromine. Bromine belongs to halogen, right? Group 17. So the valency of group 17 is 1. Now silicon is 4 and bromine is 1. Now cross multiply. Just cross multiply. That means the compound should have 1 silicon and 4 bromine. So what could be the formula? SiBr4. Okay, this is how we have to find out the compound formula of the compound of each elements that is being combined to give the thing. Got it? So now let us move on to the second topic of this chemical property, that is chemical reactivity. Chemical reactivity. So let us take the periodic table. Okay, this is the periodic table, empty periodic table. On moving down the group, we know that the ionization energy and electron gain enthalpy increases, right? Decreases. Across the period, both of these property increases. Okay. The decrease on moving down the group indicates that the metals can easily lose the electron. If the ionization energy is very, very less, it denotes that we can easily remove the electron, right? Very less amount of energy is enough to take out the electron from the group 1 element. Now the non-metals, they have the very high ionization energy value. It means that it is very, very, very difficult to remove the electron, but we can easily add the electron to that system. So non-metals can easily gain the electron and metals can easily lose the electron. Okay. Now on moving down the group for metals, the reactivity increases. The reactivity increases, and for non-metals, the reactivity decreases. And if I want to talk about the trend across the period, reactivity, chemical reactivity of metals decreases across the period, and the reactivity of non-metals increases across the period. So this is the trend that you have to keep in mind for reactivity of metals and non-metals. Got it? Now coming to the next property, that is the nature of oxides. Nature of oxides. So mostly the group 1 elements, metals, they react with oxygen to form the basic oxides. For example, sodium, when it reacts with oxygen, it forms sodium oxide of formula Na2O. But non-metals, the right side element, when they react with oxygen, they form acidic oxides. Example, Cl2O7. So why the left side elements are forming basic oxide and right side elements are forming acidic oxide? And also, what about the elements which are present in between? In between, some at the center of the periodic table, we have some elements, right? So those elements, what they will do, they will also form oxides, but those oxides are amphoteric oxides. They are forming Amphoteric means they can act as a base as well as an acid. Aluminium and arsenic, they belong to this group 13, right? So here boron, aluminium, gallium, indium, thallium, and here nitrogen, phosphorus, arsenic, antimony, bismuth. So these elements, they are forming amphoteric oxides. And also we have some neutral oxides. Those are carbon monoxide, NO, CO, and N2O. So these three oxides are neutral. So because of this, group 1 elements are called as reducing agent. Okay. And group 17 elements are called as oxidizing agent. So group 1 element oxides are called as basic oxide because when I put this oxide in the water, it produces a base. If I put this sodium Na2O in water, it will produce NaOH. Sodium hydroxide will be produced from this. So that's why it is called as basic oxide. Now Cl2O7 is called as acidic oxide because when I put this compound in water, it produces HClO4. It produces 2HClO4. Okay. And HClO4 is called as an acid, perchloric acid. And sodium hydroxide is a base. Okay. So because of this only, they are getting the corresponding names. There are 4 different types of oxides: acidic, basic, amphoteric, and neutral. You have to study these types and the examples that is given under each oxide, because the questions will be asked in match the following type from this. Okay, so have a look at it. Very easy. And coming to the relation, basic nature of oxide is directly proportional to the metallic nature. Basic nature of oxide is directly proportional to the metallic nature. On moving down the group, metallic nature increases, so the basicity of oxides also increases. Basic nature of oxides also increases. Okay, so if I want to compare, let me take a second group element. Okay, so this is beryllium, magnesium, calcium. So calcium oxide is more basic compared to magnesium oxide. Okay, because the basic nature of oxides increases on moving down the group. Acidic nature of oxide is directly proportional to non-metallic nature. So across the period, non-metallic character increases, okay, and acidic nature increases. So if I want to compare phosphorus, silicon, chlorine, okay, these elements. So chlorine is the more non-metallic thing, okay, and that is more acidic also. If I want to compare the acidity of phosphorus oxide and chlorine oxide, obviously Cl2O7 is more acidic compared to P2O5. Okay, and the sodium oxide, basic monoxide, and Cl2O7 is the most acidic oxide. Got it? So these two things we have already discussed in the previous slide. Now let us move to one question. Considering the elements, find out the correct order of their chemical reactivity in terms of oxidizing property. Oxidizing character, just now I have told you, it increases from left to right. Okay, so it increases. So the decreasing order of property is fluorine, oxygen, nitrogen. When you compare fluorine and chlorine, fluorine will have the highest oxidizing property compared to chlorine. Got it? So comparing the oxygen and chlorine, oxygen will have the highest oxidizing nature. So the correct order would be option B. Option B is the correct order. Okay, fluorine is highly electronegative in nature. It is more non-metallic, so it is having the highest oxidizing property. Okay, so let me go to the last topic of this lesson, that is anomalous properties of second period element, the unique nature or the different behavior of the second period element. So I have taken group 1 and group 2. Here lithium and beryllium belong to the second period, right? So the chemical properties of these two elements, they differ from the rest of the elements in its group. Okay, this is the second period element. So it is going to behave differently compared to its group members. Okay, suppose if I want to take one example, these two elements, they form only covalent compounds, whereas its group elements, they form ionic compounds. They form compounds with pronounced covalent character, but the other elements of this group, they form ionic compound. Sodium chloride, potassium chloride. So they are ionic in nature. But lithium chloride, it is covalent in nature. So why? What is the reason for the anomalous property of the second period elements? Already we have discussed this in detail in P block elements lesson. So let me just recall it once again, okay, with this lesson. So what is the reason? The first reason is because of its small size. Because of the small size. When I compare lithium, sodium, potassium and rubidium, actually they are group elements. Lithium is having the very small size. So because of that small size, it is forming the covalent bond, whereas the other elements are forming ionic bond. And the second reason is high electronegativity. When you compare nitrogen and phosphorus, nitrogen is the second period element. Phosphorus is the third period element. Nitrogen is highly electronegative in nature. So it will pull the electron towards itself so easily. Okay, phosphorus cannot pull the electron towards itself so easily. So this is the second reason. And the third reason is absence of d orbital. We already discussed this, no? All these second period elements, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, all these second period elements, they have only 1s, 2s and 2p orbitals. Okay, whereas when you go for third period elements, that is sodium till chlorine, they have 1s, 2s, 2p. Along with that, they have 3s, 3p, 3d also, because they are third period. They will have third shell, but second period will have only second shell. So in the second shell, we do not have d orbital. Third shell, from third shell only d orbital starts. Okay, because of the absence of d orbital, they behave, second period elements behave differently compared to the other thing. Okay, now coming to some more information about this. The second period elements, they have the inability to expand its covalency. Because of the absence of d orbital, the second period element can form only very few number of covalent bond. For example, if I take boron, BF4 minus, boron is forming only 4 bond. But the boron group member aluminium is forming 6 bond. Why? Why boron cannot expand its covalency beyond 4? Because it does not have d orbital. Boron does not have d orbital. It does not have space to accommodate 6 pairs of electrons. But aluminium has d orbital, and that's why it is expanding its octet and forming and gaining 6 electron pairs and forming 6 bonds with fluorine. Okay, inability to expand its valency. And the next topic is inability to form multiple bond. Second period elements can form multiple bonds, single bond, double bond, triple bond. For example, nitrogen. Nitrogen can form 3 bonds, right? N2 molecule. N triple bond N is nitrogen molecule. So here, if you see the overlapping, this overlapping region, it is very, very high. Means strong overlapping. Because of the very small size, they can come in contact with each other and they are forming the strong overlapping. But the third period elements like phosphorus, if you see the overlapping region, you see it is very, very less, right? Because of the big size of this orbital. So the overlapping area is very small. So the overlapping is very weak between the p orbital. Second period elements, not only nitrogen, carbon will form multiple bond with another carbon, carbon, oxygen, oxygen, oxygen. So like this, many atoms, they are forming multiple bonds between them, and those multiple bonds are very, very strong for the second period elements. Got it? Now coming to the last small topic, diagonal relationship. So second period elements and third period elements, they are diagonally related with each other in some of its property. Suppose if I take lithium, lithium is diagonally related with magnesium and beryllium is diagonally related with aluminium. Boron, silicon. Carbon, phosphorus, nitrogen, sulfur. So like this, second period and third period elements, they are diagonally related with each other. So they are having diagonal relationship with each other. In case of size, in case of electronegativity, they both are having somewhat similar value among them. Okay. So for example, in case of size, you see lithium and magnesium, both are having approximately around 150, 152 for lithium and 160 for magnesium. Almost similar atomic radius. Not only radius, both of them are very hard. Lithium and magnesium are very, very hard. Both of them form nitrides. Both of their hydroxides, they decompose on heating. Okay, they decompose on heating. And when you see the metallic radius and ionic radius, both of them, they are having here, metallic radius is 152 and 160, which is given here, and ionic radius is also similar, 76 and 72. Okay, after losing one electron, lithium will form Li plus ion and magnesium will form Mg2 plus ion, right? So that ionic size is also almost similar to both of them. Got it? So this is the diagonal relationship concept. Now let us move on to one question. Are the oxidation state and covalency of aluminium same? So how to find out the oxidation state of this element of aluminium? Let me take this aluminium as X, and for each chlorine I have to give -1 charge. Water is neutral, so it is 0, 5 into 0 is 0, which is equal to the charge on the complex. Charge is +2. Okay. When you bring this -1 to the other side, it will be +1. So X is equal to +3. So the oxidation state of aluminium is +3. Covalency of aluminium, oxidation state is +3. To calculate the covalency, I have to draw the structure. So aluminium is there and it is bonded with 1 chlorine and 5 water molecule. 5 water molecule, right? So what is the covalency? So it is having 6 covalent bond around it. So the covalency of aluminium is +6. So therefore, the oxidation state and covalency of aluminium in this compound, they are not same. They are not same. Got it? This is how you have to find out the oxidation state and covalency. Now let me summarize the chemical property and its trend. So chemical reactivity is highest at the two extremes of a period and is lowest in the center. The left side element and right side element, they are highly reactive in nature compared to the elements which are in the middle, okay, of the periodic table. And highly reactive elements do not occur in nature in free state. They usually occur in the combined form. Suppose for oxygen, oxygen is highly reactive. It will not exist as O. It will exist as O2. So they are reactive. So it exists in the elemental form, in the combined form. And oxides formed by metals are basic. That is the left side elements, they form basic oxide, and the right side element, non-metallic elements, they form acidic oxide. So here you can see sodium is left side, metal, so it forms basic oxide. Chlorine is at the right side of the periodic table, that is non-metallic, so it is called as acidic oxide. And these two are amphoteric oxide, and the last three, these three are neutral oxides. So this part is very important. I already told you it will be asked in the match the following part. Have to keep in mind. Okay. So with this, the periodic table lesson gets over. Okay. So in the next class, we can start up with the new lesson, chemical bonding. So if you're having any doubts from this lesson, you can ask me. Otherwise, we can meet up in the next session with a new lesson. Okay, if you're having any doubts, just let me know. No doubt? Okay then. Thank you so much for listening the lecture. Meet you all in the next class. Bye-bye. Thank you. Take care.